Okay, so today we're going to look at the movement of gases, how gases spread around the room. There's a couple of words they use to describe that movement. First one you used last year in bio class, diffusion. You talked last year about diffusion across a membrane, but we're going to talk about gases diffusing. So what all diffusion has in common is it's moving areas of high concentration to low concentration. So things spreading out. Okay? Perfume molecules spreading across the room. They're at high concentration where you spray them on your body, and they spread out and you get lower concentration. That's one kind of movement, diffusion. Okay. The second kind is effusion. Effusion is moving from areas of high concentration, low concentration, but through a tiny hole in the container. So it's still from high to low concentration, but now we're not just letting it expand freely like we do perfume, we're making it escape through a hole. And the reason why we teach these two together because they both depend on the same thing. In today's simulation, you'll see that. Okay? And what they depend on is the speed of the molecules. Faster the molecules, both those happen. Faster the molecules, faster both those happen. They spread out faster and they escape faster. So we need to talk about how fast they're moving, which means we need to think about temperature. The temperature was average kinetic energy. But it was the average kinetic energy. There was always slower molecules and faster molecules, but we talk about the average. But speed is only one part of kinetic energy. There are two parts to kinetic energy. Okay? Kinetic energy, the energy it has because it's moving. I mean, if a semi and a motorcycle going the same speed do not have the same amount of energy. Well, I mean, there's a big difference stepping out in front of a truck doing 10 miles an hour and stepping in front of a skateboard doing 10 miles an hour. One of them is going to transfer more energy to you. So that mass affects kinetic energy. That to have the same kinetic energy does not mean that you're moving the same speed. To have as much speed as a semi, the motorcycle would have to go much, much faster. So at the same speed, the motorcycle has less kinetic energy, less mass, less kinetic energy. But in this room, or in a place where at the same temperature, they have the same kinetic energy. So in order for a small molecule, a small piece and a big piece to have the same kinetic energy, the small piece has to be moving faster. So smaller particles have to have a greater speed to have the same kinetic energy. In order for a car to hit you as hard as a truck, the car's got to be moving faster. These aren't cars and trucks, they're little tiny molecules we can't see, but the same rules apply to them. At the same temperature, smaller particles move faster. And that's where I want to stop today with this, because I want you to see these effects in the simulation I've assigned. So from here I need you to move, go complete the assignment, the gas simulation assignment. And then tomorrow, just to check where everybody's at, I'm going to post a quiz that you'll take online. It won't be a Google form, I'll do it a different way. But the instructions will be there tomorrow. And I need a check to see that everybody's keeping up and see where I need to focus myself. So with that in mind, go ahead and complete that assignment and turn it in, and have a great afternoon.